All right, good afternoon. This is Rakshith Krishnappa from Intel. So in this tutorial, I will be presenting the DPC C++ new features. In the previous tutorial, we just saw the basic program structures of DPC C++. And this session is mainly focused on what are the new things that are added to the DPC C++ language. Right. So the main learning objectives of this tutorial is to use new features like unified shared memory to simplify heterogeneous programming. We will also understand the advantages of using what are called subgroups in DPC C++. And finally, we will also look at advantages of using the DPC C++ library for heterogeneous computing. So this is just a recap on what we learned in the previous tutorial. So mainly DPC C++ is C++, SYCL, and then some new extensions. So this particular tutorial will mainly focus on these extensions that are added on top of C++ and SYCL. So mainly, what are these extensions? These are mainly to enhance productivity. So this is mainly to simplify the language and also to reduce the verbosity and programmer burden. And the second main goal is to enhance performance. This is by giving programmers control over program execution by mainly enabling hardware-specific features. So we will look at an example of these two goals mainly for the extensions. And also, we have to note that DPC++ is a fast-moving open collaboration that will feed into the existing SYCL standard. The open source implementation is available on GitHub, and anybody can contribute to it. So again, in this particular tutorial, we will look at some new features in DPC C++. Today we will look at what is unified shared memory, and also we will look at subgroups. So the main goals are to simplify programming. So we will look at how it simplifies by using unified shared memory, and also we will look at how we can achieve better performance by using what's called subgroups. So let's look at unified shared memory. So unified shared memory is a pointer-based approach to memory model in heterogeneous programming. So mainly in the previous tutorial, we looked at buffers and accessors. So this unified shared memory is mainly, it complements the buffers and accessors way of managing memory. It just provides a pointer-based approach. So why do we need to use unified shared memory? So we know that buffer memory abstraction is powerful way to express data dependency. However, using buffers and accessors is a new concept that is not familiar to regular C++ programmers. So if you are trying to migrate your code to DPC C++, using buffers may actually be a burden to programmers. So that's where unified shared memory comes into picture, where it simplifies porting to an accelerator. It gives a desired level of control for programmers. And the important thing to note is unified shared memory is just complementary to buffers. As a programmer, you are free to use either unified shared memory or use the buffers and accessors way of programming. So this particular diagram here gives you a picture of developer view of unified shared memory. So on the left, you can see how typically a programmer would see the host memory and GPU memory as two separate memory objects. But whereas if you use unified shared memory, the host memory and GPU memory can be referenced with the same data object, either from CPU or GPU. So now let's look at how that actually works in a very simple example that uses unified shared memory. So here you can see that in the simple code example here, we have this new function called malloc_shared. So this is what will set up unified shared memory, where we are specifying a data object, and we are saying this is a we're using this malloc_shared function, and we are passing in the n number of objects, and then we are also passing the queue parameter here. So this mainly tells that memory is being shared with the host side and also whatever device is selected by the queue here, right? If we are using a GPU, so the data object will be can be accessed from the host as well as on the GPU. On the second step, you can see that we are actually initializing this data object with values of 10 on the host side. And then the next part is the kernel function. So here you can see that the same data object is actually accessed on the device side, and it's being modified by adding 1 to each one of the elements here. And then finally, once the kernel function is completed and we wait for completion, you can see that the host can directly print out the data object. And this particular example will actually print out the value 11 in each one of the items in data array. Right. So you can see how simple this particular code example is when using unified shared memory. If you want to compare the same example using buffers and accessors, you can see in the next slide here. This is an example, same example that's actually using buffers and accessors. Here you can see that we set up a host memory, which is only accessible on the host, and we initialize the values in that memory with values of 10. And here, since we are using buffers, we create a buffer called myBuffer for this data object that was just initialized. And then you can see that we also have to create an accessor with the read-write permission. And then the device can actually modify this accessor. And once this kernel function goes out of scope, then the buffer is destructed, and then memory is copied back to the host, and then finally you can print out. So you can see that compared to the unified shared memory example, this has a lot more steps involved, but both of them work the same. So here is a syntax of how unified shared memory is set up. You can see that there are two ways you can set up. One is a simplified way. All you have to do is malloc_shared, and then you specify the type of the item that's used in the array, and then we pass in the size and as well as the queue, which mainly is used to specify which device the data is shared with. And then there's also a different way to initialize using more C++ or C style malloc. So here you can see that any C++ developer is familiar with this kind of declaration here. The only difference is instead of using malloc, we use malloc_shared, and then we pass this extra argument, which actually specifies which device the data is shared with. So mainly there are three types of unified shared memory. So one is device allocation, host allocation, and then there's a shared allocation. So the device allocation is mainly used when we need explicit control of memory movement. Here, if we do device allocation, the allocations is on the device and is accessible only on the device. The host does not have access. If you use host allocation, the allocation is done on the host, and it's accessible both on host and device. And if it's shared allocation, the allocation does not can migrate between the host and device, and it's implicitly done depending on where it's being accessed. So we will look at examples for all these different types. So let's look at the first example where we use device allocation, and this is more of an explicit data transfer. In this example, you can see that first of all, we have a queue defined, and then we have allocation on the host side called data. And then we have an allocation called data_device, which is a malloc device, which is allocated on the device. In this case, since the data_device is only accessible on the device, we have to first copy the contents of data into data_device. So the memcopy command will actually copy it. So at this time, the memory is copied from host to the device. And once the data is on the device, now you can actually modify that data object on the device. All you have to do is access data_device and modify. And once this particular compute function is complete, then further we have to copy back the data from device back to the host. And that's what this third kernel function is doing, where it's copying the memory back to the host. And then finally, the data will be available on the host to print. So let's compare more implicit data transfer. This is the example we saw before. If we use malloc shared, you can notice that the same data object can be used on host as well as on the device. And you can notice that all the data transfer is implicitly done. So we don't explicitly say when we are copying memory from host to device and device back to the host. So all that memory copy is implicitly done. So all you have to focus on is writing your compute kernel function. And we can actually look at these two code examples on the dev cloud. So let me switch over to the dev cloud here. Hopefully you can see the screen. So this is the same tutorial we downloaded in the previous session. So if you go to the welcome page, module 3 is what we will be looking at, which is unified shared memory. So if you click on that, so all the content that I'm sharing on the slides is actually available in this document right here. So you can learn about what is unified shared memory, the different types of unified shared memory, how it's declared, and then let's look at these two examples. So here, unified shared memory with implicit data movement. So in this code example, you can see that we are doing malloc shared and allocating memory, which is shared between the host and the device. And then you can see that we initialize the values of the array with values from 0 to 15, this example here. And then finally on the kernel function, we actually multiply each value by 2, and then we wait until this device computation is complete, and then the data is automatically copied back to the host, and then the host can actually print out the output. So if we want to execute this particular code, we first run the cell to save the file, and then if you click on the build and run cell and run this particular cell, this this program will compile and run on a GPU device. So this should take about 20 to 30 seconds, and we should see the output of this particular example.
Rakshith, how do you make sure the data, this q and this q.parallel4 is run on device and not on host?
So when we execute, we will, since we are printing out the device name, right? When we say q and then q get device, so this will actually be printed here. Now you can see that this particular device it ran on was actually on the graphics.
Okay, thank you.
Right. So here you can see that the data was initialized from values from 0 to 15, but then the device actually modified it by multiplying by 2, and you see those output here, right? So this is an example of using malloc shared and implicit data movement. You can see that we didn't write any code to move the data between host to device and device back to the host. So let's look at more explicit way of using unified shared memory. So here you can see in this code example, it's the same example where we are multiplying each values by 2. But here you can see instead of using malloc shared, we are using malloc device. That means this particular data object cannot be accessed on the host. So in this case, we have to first do a mem copy from so that it copies the contents of data into data underscore device. And then you can run this kernel function, which will multiply each value by 2. And then finally, once that is complete, you can copy the data back to the host so that you can print out the values. So let's run this as well, and then check if we can see the same output. So this mainly using malloc underscore device will give you more control of when the data is actually being moved, and you can, depending on how complex your program is, you can control when exactly you want to do all the data transfer. So this code example just completed, and you can see that it prints out the same output as the previous example. The only difference is it's using malloc underscore device versus malloc underscore share. So let me switch back to the slides again. So now that we have looked at both implicit and explicit, let's look at when to use unified shared memory, right? So the SYCL buffers are powerful. You can use it if you are familiar with buffers and accessor concepts, and if the abstraction applies cleanly in your application. It is a learning curve because buffers and accessors are new concepts in the SYCL standard. So if you're familiar, obviously you can continue using that. Where unified shared memory is an advantage is usually when porting C++ code to DPC++, right? So usually C++ code will already have mallocs in the for memory allocation. So all you have to do for using unified shared memory is convert the mallocs to either malloc device or malloc shared. So that way, easily with minimal changes, you can actually port C++ code to a DPC++ code. And also note that we looked at shared allocation and device allocation, right? So usually when porting a code to get functionality quickly, it's always useful to use shared allocation so that you don't have to write code to move the memory from host to device and device back to the host. But you also have to note that shared allocation is not intended to provide peak performance because all the memory movement is done implicitly. So if you do want to tune for performance, it's always recommended to use explicit USM allocations. So this is the malloc underscore device example that we showed. So in summary, unified shared memory, we learned what is unified shared memory, and we also learned what is implicit and explicit data movement. And there is also a lot of tutorial on how to handle data dependency when there are multiple multiple kernels used in the same application. So let me switch back to the slides here. So there are more advanced topics here. If you have multiple kernels, how to handle dependencies. So here, mainly we have code samples showing similar examples where we initialize an array with value of 10, but instead of having one kernel function, we have 3 kernel functions here. So in this case, we have the first kernel function is adding 2, the second one is adding 3, and the third one is adding 5. So the final output should be 20, right? So, but then an important thing to note here is that when these 3 kernel functions are submitted, these 3 may be submitted at the same time. Since they have a dependency, since the same data element is used in all 3 kernel functions, you have to make sure that there is some data dependency handled. You have to wait until the second, wait for the first kernel function to be complete before the second one can be started, right? So there are various ways you can do to do this by adding wait commands here, so that this will wait until each kernel function is complete. So this is one way you can do data dependency. This is something you can try on your own, try executing these code by doing data dependency. So this documentation here provides different ways you can do data dependency. If you're looking for solution, there is a solution file right here. So if you click on that, it will show you what is the best way to handle dependency. Here you can see that we have used something called the queue property, called in order queue property. So this will make sure that all the different queue submits are actually done in order, one after the other. So that's one way to handle dependency. So there's another example here too, where we have 2 data allocations, data 1 and data 2. And you can see that the first kernel is actually modifying data 1, and the second kernel is modifying data 2. So in this case, these 2 kernels can actually execute at the same time, since there is no dependency. But whereas the third one has to wait until 1 and 2 are complete. So you can look at the solution for this one as well. Here you can see that the slight modification we've done here to handle this dependency. We have seen that, you can see that we have auto E1, so we are actually capturing the event for each one of the kernel functions, E1 and E2. And when we run the third kernel function, we actually pass this E1 and E2 as the parameter. So this is just telling wait until E1 and E2 events are complete before you actually execute this one. So when you run this particular example with the dependency put in, it will actually give you the right output. So this is something you can try out. The documentation explaining each one of the different methods to handle dependency are right here. So let me switch back to the slides here and move on to the next topic. So let's look at subgroups. So on many modern hardware GPUs, usually a subset of work items in the work group are executed simultaneously or with some additional scheduling guarantees. So these subsets are usually called as subgroups, and leveraging this subgroup will help you to map execution to lower level hardware, and this will help you to achieve higher performance. So let's look at how this is done. So let's just recap ND range kernels, right? So ND range kernels is a way to express parallelism, which will enable you to map execution to what's called compute units on the hardware. So in this example, you can see that, let's say this is your entire iteration space, which is 8 by 8 by 8, three-dimensional space. And we have divided a smaller block size of 4 by 4 by 4. And we do this so that we can map executions to the hardware. So let's look at an example of Intel Gen 11 graphics schematic here. You can see that the hardware itself has a bunch of these blocks called compute units, right? So when we have a workload, we can divide it into smaller blocks so that it will fit on each one of these compute units, and so that we can divide into a bunch of blocks and then execute simultaneously on all these compute units. So that is what workgroup was. And then with DPC++, we introduce another way of grouping. So each one of these individuals workgroup can be further divided into a smaller group. That's what you see in green here, called subgroup. So this will actually map into map to a vector hardware on the execution unit. So this will give you much more control of how your program is actually mapped to lower level hardware, and you can achieve better performance. So let's look at what the subgroups are, right? So mainly one of the biggest advantage of subgroup is that if you can communicate with the next item in the same subgroup by using shuffle operations with without using any explicit memory operations. So let's say you're on the first work item here, you want to access the adjacent work item. Usually the way to access it is you have to go through the global memory, then read, and then read the memory from global memory. So whereas if you use subgroups, since the entire subgroup is on the vector hardware, you can actually use a shuffle operation. So that way you are not actually doing a lot of memory access. So this will reduce the latency and will give you better performance. And the other main advantage is subgroups can synchronize using subgroup barriers and guarantee memory consistency, right? So that's another advantage, since all of the items within the subgroup are on the same vector hardware. And finally, for each subgroup also have access to what's called subgroup collectives. So these are fast implementation of some common patterns. So we will look at an example of these subgroup collectives. This will help you to do fast addition or find the maximum or minimum of items within the subgroup. So here is complete ND range execution. So how, for example, if you have the entire iteration space of 8 by 8 by 8, each work group is divided into 4 by 4 by 4, and then you can see that the ones in green will be the subgroup that will map to a vector hardware, whereas this entire block, orange block, will map to compute units on the hardware. Now let's look at how a subgroup handler can be defined. So here you can see that we use the regular ND range way of defining a kernel. We have the full size, global size of n, and then b is the workgroup size, the block size. If we want to get the subgroup, we use the Intel subgroup SG, and then item.get subgroup will actually get the handler from the ND item, right? So once you have the subgroup, you can actually query for more options, and you can also make use of the shuffle operations and collective functions that we mentioned. So let's look at some examples of using simple examples how subgroups can be used. So let's look at doing simple queries for subgroup, right? So there are various query functions, methods that we can use. So for example, a get local ID will return the index of work item within the subgroup. Get local range will give you the size of subgroup. Group ID will return the index of subgroup, and also the group range will give you the number of subgroups within the parent work group. So in this case, in this example, you can see that we are trying to just print out all the subgroup and its ID and size. Here you can see, I think we are assuming the size of 64. You can see that the output that displayed is the subgroup size is 16 in this case. So there are 4 subgroups of 16 within this work group, and you can see that the index is also printed out here. So it's showing 1 of 4, 3 of 4. So the important thing to note here is that each subgroup is executed out of order. So there should not be any dependency between the 2 subgroups. So it can execute in any order. And then finally, you can compute once the subgroup level is computed, then you can actually combine the results. So we will look at some more examples that make use of subgroups. So we talked about shuffle operations, right? So this is one of the most useful features of subgroups, is the ability to communicate with work items without any explicit memory operation, right? So in this case, we are showing different shuffle operations. So here you can see in this particular example, we are doing a shuffle XOR for this data item. So here you can see if the subgroup has values from 0 through 7, and we are doing shuffle XOR. Shuffle XOR, essentially what it's doing is it gets the value of the adjacent element, and we are swapping it in this case because we are saying data of I equal to shuffle XOR of data I. So in this case, the value of 0 will actually get the value of 1 here, and then the value of 1 will be replaced with value of 0. So that's what's happening. So mainly the important thing to note here is that when you use shuffle, this particular value of 1 does not go through the global memory, and then it does not go through the global memory. Instead, it just does a shuffle operation to read the value. So that way, you're reducing the latency there. Okay, and finally, we also talked about this subgroup collective function. So this is mainly some commonly used functions are available as library functions here. In this case, we have a plus function, which is mainly does addition of all the elements within the subgroup, or there's also other collective operations that are available, like maximum or minimum. So in this case, if you use reduce and use the plus operator, then this will mainly add all the values of a subgroup, and it is actually highly optimized function that uses lower level hardware, right? So we will look at live example of this one. So let me switch over to the Dev Cloud again. So in the same welcome page, if you go to module 4, we have some examples of subgroups in this one. So this document has all the details that I went through in the slides. Shows how the subgroups and workgroups are mapped to the hardware. And then we have all examples here. So let's look at this shuffle example that we looked at, right? So in this example, we have a global size of 256, and we have chosen a workgroup size of 64. And then in the kernel function, you can see that we have we are defining SG as a subgroup. And then in this case, we are actually doing a shuffle XOR on this subgroup, and mainly swapping the adjacent elements and then printing out the output. So if you want to try this example, first run this out to save this path, and then let's build and run. And then this should take about 20 seconds, and then we will have we should have an output. Yes, taking longer than expected. Let's see. Yeah, so just printed out the output. And here you can see that we are first printing out the initialized values, which is values from 0 to 255. And then you can see that the device side, we actually did a shuffle operation, and you can see that 0, 1 actually became 1, 0, and then so on. 2, 3 becomes 3, 2. So in this example, the important thing to note is that while doing the swap, the data wasn't actually copied from global memory or local memory. It used a shuffle operation to actually read the adjacent elements. Great. So then we also have the collectives example that we just looked at, which is all we're doing is we're initializing 256 elements with values of 1 to 256, and then we use a reduce function to actually compute the addition of each subgroup. So let's run this example. So you can also try a different function. Instead of plus, you can try the maximum and minimum, which will actually give you the maximum or minimum within that subgroup. Let's wait a few more seconds. So here in this example, you can see that we have the initial values from 1 through 256. And then you can see that for each subgroup, the addition is actually printed out in the first element, which is what we did here. So you can see that we calculate the sum for each subgroup, and then we assign it to the very first item in the subgroup. We actually assign the sum. The rest of the values we assign 0. So that's what you see here. So if you added from 0 through 30.1 through 32, the value is 58, and if you add from 32 to 64, you will get a value of 1552. So that's what subgroups will allow you to will allow you to use lower level hardware to do your computation. So let me switch back to the slides here. So just a summary of what we looked at. So we looked at what are subgroups, why are they useful, and we also looked at simple subgroup shuffle operations and subgroup collectives. So the next topic that I was going to cover in the last 15 minutes was
data. Rakshith, there's a question. So this depends on in the USM, right? Depends on and wait. These are blocking calls, right? So the question is there any non-blocking way of handling things? So
Yeah,
this,
so there is, so let me go back to the dependency part, right? No, I don't have it here. Yeah, so the important thing to note here is that if you use the wait wait method, so this is a blocking function on the host, right? So that will actually, so that is not recommended to use, but it's a good way to test the functionality. But if you use depends on will, it's a blocking function on the device side, but the host is not blocked here. So let me open up an actual example. So let's say we have this particular example, right? We are using a depends on here. So this one is not really a blocking function on the host side. So if you do a mem copy, so this will run, and at the same time, the submit will happen, but then on the device side, there is a depends on E1, right? So on the device side, it waits until E1 is complete, which is the event for the first kernel function. Whereas if you use the wait right here, so this will actually block the execution on host, right? So it will just pause right here and then wait until it's complete, even before the submission happens. Whereas instead of using wait, if you use depends on, this particular, the next kernel function is actually submitted, and also the third one is also submitted, right? But then it actually waits at this point when it hits depends on. Hopefully that answers.
okay, thanks. Yeah.
And the same thing with the other one, the in order queue property, which is I think right here. So this one too, right? So this, using this property, again, there is no, it does not block on the host side, but it's mainly all three are submitted, but then it just makes sure that it actually executes one after the other. Yeah. So let me, okay, let me move on to the final topic in the last 15 minutes. So let's talk about data parallel C++ library, right? So data parallel C++, or we call it oneDPL, is a companion to the DPC++ compiler and provides an alternative for C++ developers who create heterogeneous applications. So it's an API based on familiar standards and maximizes productivity across CPUs, GPUs, and FPGAs. So mainly the data parallel C++ library consists of three components. It's the standard C++ APIs, and the parallel STL algorithms, which are now extended for heterogeneous computing. And also there are some extension APIs which are added on top of these through standards. So let's look at a simple example, right? So let's say we will look at how it maximizes productivity and performance on heterogeneous devices. So let's say if you want to compute on the host, a simple compute like sorting a vector, we would use something like this, sort, and then we use v_begin, b.begin, and b.end, right? So let's say you want to extend this to work on GPU. In this case, you would, all you're doing is you're using the same sort example, except you're actually passing in execution policy that tells that the library function should be executed on the GPU. So we define a queue and say that the queue should actually select the GPU, and then we use the same sort function where we pass in v.begin and v.end, and then all you have to do is like pass this execution policy. So this will make sure that this particular function is actually executed on the on the GPU rather than running it on the CPU. Right, so that is what Data Parallel C++ library is. So let's look at a simple DPC++ code example, which uses buffers and accessors. In this case, you can see that we have defined a queue. We have a vector of size n, and then we create a buffer for this vector, and then in the actual kernel function, we create a accessor for the buffer, and then we actually give it a value of 20, right? So in this example, you can see that this whole block of code that is used to create a buffer and create a kernel function can actually be replaced with just one line of code when we use the library, right? So this just makes, you can see that anything that's in this yellow box is actually all new concepts for a C++ programmer, right? So buffers and accessors and then submitting to a device is all new concepts. So to make it easy, the library will actually help you to replace this entire thing with one line of code. And you can see that we are using a fill function, which is what we were doing in the previous example here. We create an accessor and we were filling it with value of 20. Here, instead of doing that, we just use this fill function. The important thing we are doing here is specifying execution policy, saying that it should execute on the GPU, and we use the same pass in the vector begin and end, and then the value we want to fill it with, right? So in this way, you can see that using the Data Parallel C++ library will make it very easy to do heterogeneous programs. So let's look at a full example of how Data Parallel C++ library can be used. Here you can see that the library function we use has an execution policy. There are two header files that need to be included. One is the oneAPI DPL algorithm, and then the other one is execution. And then the most important thing is this device execution policy, which tells where the library function is executed. Right? So if you don't have this one, it will just run on the CPU. So how does this library function work? So a parallel STL algorithm can be called with ordinary iterators, but then the steps that happen when you call a execution policy here is that a temporary buffer is created behind the scene, and then the data is copied over to the device side, and then after processing on the device side, the temporary buffer, the data is copied back. So all this work of creating a buffer and then moving the data from host to device and device back to the host is all implicitly done when you use the library functions. Right? That's how typically the library function works. So now let's look at an example. Let's say if you have to use multiple library algorithms, right? So in this example, I think what we are doing here is we're using two library functions. One is for each, and then the other one is sort. So we have a vector defined 2, 3, 1, 4. The first library function is actually multiplying all these values by 2. And then the second one is actually sorting them, right? So this particular program here works because you have two functions, but the important thing to note here is that between each one of these library operations, the data is actually copied from host to the device, and then it computes this particular for each function, and then the data is actually copied back to the host. And then when you access the when you run the second algorithm, again, the memory is moved from host to device and device back to the host, right? So this works, but then there is a better way where we can actually minimize the number of times memory is copied back and forth. To minimize these copies, we have something called as buffer iterators. Okay? So this is important to use when you want to optimize your applications to limit the number of memory transfers. So let's look at this example here. So here in this example, it's the same example where we initialize a vector with values 2, 3, 1, 4, and we create a buffer in this case, right? And then we create what's called the buffer iterators, where we create buff underscore begin, which is not, we use this namespace, oneAPI DPL and begin, and then include the buffer. So this will give the starting point of the buffer and the end point of the buffer. And then if we use the two parallel STL functions for each and sort, in this case, it's actually, instead of using vector iterators, instead of using v.begin and v.end, we are actually using the buffer iterators, right? So in this case, these buffers actually remain on the device memory, so that both of these are calculated, functions are calculated, and when the scope ends here, when the scope ends, the memory is copied back to the host, and then you can print out the output. So we will look at this, execute this on the dev cloud. So before we move on to the next one, let's look at one final example here. So this is, we learned about unified shared memory. So you can also use unified shared memory pointers when using the library. So it's a very similar example to the fill example we saw previously. So where we define a malloc shared, which is unified shared memory. And here you can see that the data pointers can be iterated just by using the starting data value, and then we add +n, and then that will give you the end of the data object here, and then the fill will actually fill values of 20 between in this entire array value. The important thing to note when using USM is to use this q.wait so that the data is not corrupted before the host can actually read it, right? So this wait will make sure that this fill function is complete before you can actually print out the output. So now let's quickly look at a few examples in the library. So in this same welcome document, if you go to module 7, we have a data policy ++ library introduction. So here you can see all the documentation that you saw in the presentation. So let's look at one of the simplest example here. So this is the fill example. So where we have a vector of size n, and then we do a fill operation, fill the values with value of 20, but then we also specify execution policies saying that this should actually run on a GPU, right? So let's run this example. So let me save this file, and then if I execute the cell to build and run, so this should take about 20 seconds and should give you a vector of size 4 with values of 20. So let's wait for that output. Let's see if the kernel is still running. Okay, the deplog usually times out after 4 hours, so I think I might have run into that issue. So let me just restart my deplog. Okay, so let me go to the simple example and then run that again. So here you can see that it completed execution, and you can see that this was actually computed on the Intel Gen graphics device, and then you can see that it filled with the value of 20 on the device side. That's what we did here. So similarly, so this particular notebook actually talks about the execution policy, and then an example that's showing multiple oneDPL algorithms where we directly call two functions, one after the other, and then it actually shows that what's really happening if you call it this way, where the memory is copied from host to device and then device back to host, and then it's actually copying the same back to the device again. So to avoid this is when you use buffer iterators. And this example shows buffer iterators, and also the unified shared memory example here, right? So you can execute any of these code samples and then try out these samples. And if you look at the library, there's also another example which shows how gamma correction function can be done using simple data fallacy plus library. So this is another, another tutorial you can actually run on your when you guys have time. So with that, let me go back to the slides again. Yeah. So in summary, so data parallel C++ is a standard-based and cross-architectural language to provide both productivity and performance across CPUs and accelerators, right? So it extends the SQL 1.2.1 standard with some new features. So those new features that we discussed, USM, Unified Shared Memory, and Subgroups, are part of a community project. So it's available on this GitHub page, github.com/intel/LLVM. Feel free to open an issue or submit a pull request. There's an active community around that. And that's all I had for this tutorial. So let me know if there's any final questions. If not, I'll answer all the questions that's in the Slack channel right after this tutorial.
Yeah, one follow-up question, Rakshith. So the question is, for the same depends on, right? Can host check the status on device return if there is no, that's not a blocking call, right? Can the host anytime check the status of?
Yeah, you can at the host you can use queue.wait, which will actually
That'll be a blocking call, right?
Yeah, that'll be a blocking call.
Yeah.
Yeah, usually like
yeah, any attempt we try to make a call to host, that will be a blocking call. That's what I thought too.
Yeah.
Yeah.
Yeah, I mean, if the host is depending on that data, then it has to wait, right? So that's the reason why.
Exactly. Yeah.
So in the so let's say this example here, right? So the very final kernel function will always use await, because immediately after that we are actually printing out on the host side, right? So there has to be a blocking call, because there's no other way to get the correct value unless we wait for the completion of the kernel function. But if there are multiple, and if there are internal dependencies between the inside the kernel, then we can use depends on or the in order queue property. Check on device status. Yeah, so I think the question, I'm looking for a non-blocking check on device status. Yeah, so this this particular get info function for the device will actually has a lot more information you get regarding the device. So this might actually have a status.